Hello students, previous video we discussed about the concept of finite element analysis and weighted residual problem for unit 1. Next in this unit we are going to discuss about the one dimensional problems. Before going to do that presentation, we should know that what is the meaning of one dimensional problem. When we consider only one axis, the one parameter is varying, that is called as one dimensional problems. Okay, for example, if you consider as a cantilever beam, you are applying in the x direction, then what will happen? So it is elongate the bar, or if you elongate the beam in x direction only, remaining y direction and z directions are 0. So when we are considering only one axis, that is here we consider only x axis, applying the load to get one parameter is varying rather than y and z it is 0. So that type of problem it is called as one dimensional problems. So in this unit we are going to discuss about these parameters, that is a one dimensional problem. So here generally one dimensional problem we consider as bar and beam element, and also we consider as stress element also. Okay, so that is why that this unit will be classified as three categories. One is static, dynamic and heat transfer. Okay, in statics we are classified as three categories. One is beam element, bar element, stress elements. If you are taking a problem as a beam, then you consider as one dimensional problem in FEA. Okay, similarly bar element, having a rod or having a pipe, so that type of problem we consider as one dimensional problem. So here the bar element will be various conditions will be applied while solving the problem. So that first one is no self height, second one is considering the self height, then third one is temperature effect. The next one is stress element. So stress elements in upcoming topics we discuss about the stress element. So in static condition we can apply the three categories. The another one is dynamics. So dynamics is nothing but vibration. So what is the vibration occur in bar element, and also what is occurring in beam element. So, okay, the next one is heat transfer. So heat transfer you studied in this semester of heat and mass transfer. At the time you studied with the help of data book, that is heat and mass transfer by Kodandaraman CBK. So that book would be based on that book. Based on that analytical formula you can be solved in heat transfer, that is finding of convection, radiation, and then conduction problem. For wall element, for composite pipe wall, so that type of problem we solved in heat and mass transfer. So that heat transfer it be dealt with in numerical analysis, that is for in FEA. In FEA you can be classified two category. One is bar, other one is wall. Okay, so here what we are going to calculate, here you are calculate in temperature. So what is the temperature? So if for initially we temperature applied as 100 degrees centigrade, what is the middle of the wall, what is the temperature? Then after that at the end of the wall, what is the temperature will be occur by means of convection or conduction or radiation. So that type of problem can be solved in one dimensional problems. So one dimensional problem is generally classified as bar element, beam element and truss elements. Okay, so that is why bar and beam elements are considered as a one dimensional problem, one dimensional elements. These elements are often used to model trusses and frame structures. Bar is a member which resists only axial loads. Okay, the main thing is only one axial load, that is when we considering one axis, the one parameter is varying. That is a concept. So beam can resist axial and lateral and twisting loads. Okay, so based on the condition we can be classified. Okay, so beam then next one is truss. So truss is an assemblage of bars with the pin joints, and frame is assembling of beam element. Okay, suppose if you are consider it is a bar element, Okay, so now we can I already told that the one dimension, two dimension, three dimension is nothing but your discretization process. How do you the bar or your model will be broken into several pieces, that is infinite is converted into finite elements. Okay, so that is a finite. Here we can be 5 finite elements. That is, finite is nothing but element 1, 2, 3, 4, 5. But how many loads in one element? That is 2. Okay, so for one element you having a 2 nodes, and similarly, so 5 elements you having a 10 nodes. So 1, 2, 3, 4 and 5. Okay, next, before going to solve this problem, we should know that the general concepts or general steps for FEA is first you governing the equation. That equation, it is called as a stiffness matrix equation. In previous lecture, I told that how do you calculate by means of K into U is equal to F, or F is equal to K into U. F is equal to K into U. Okay, whereas K is a stiffness matrix and U is a displacement and K is a force matrix. Okay, so that we are discussed in previous video, right? So based on that concept, we can be described in this formula. So stiffness matrix for one dimensional bar element. So K is equal to AE divided by L, 1 minus 1 minus 1 1. So we already derived this formula in unit 1 itself. Okay, you can refer it. Then A is the area, E is the Young's modulus, L is length. Okay, then stress. Next parameter we are going to calculate as stress. So stress is equal to, you generally know that Young's modulus into strain. Strain is nothing but du by dx. That is change in length by original length. Okay, so that is why u2 minus u1 is a change in length divided by L1 is a original length. Okay, for particularly for element 1. Okay, for considering element 1, that is node 1, node 2, right? The next one is reaction force. So in this problem mainly we calculated as reaction force. So reaction force, the formula is R is equal to K into U minus F. Okay, how do you derive it? Is based on the Newton's third law. Okay, every force action and it is equal and opposite reaction. Okay, based on that formula you can be solve this formula. Okay, you can derive this formula. Okay, K into U minus F. The next one is for temperature effects. Oh, and I previously told that. So these are 3 conditions. There is a bar element. We can be classified in 3 categories. One is self height consider. Next, without self height is considered. Then third one is temperature effects. Okay, so that is it for temperature effect. So suppose in a bar we can it be varying based on the temperature. So change in temperature. So at the time stress is also developed. Okay, for that reason we need to calculate. We can implement it in the force formula, E into area into alpha into del T into minus 1 and 1. So it is alpha is a coefficient of thermal expansion, del T is a change in temperature. When considering the self height, sometimes in questions they asking given as a self height of or as density of. So at the time you can be included in force formula. You can be calculated. So rho into A into L divided by 2 into 1 1 1. Okay, next we are going to see the problems. So this is for example problem 1. So find the stresses in each element and support reaction. Okay, then A1 is given, area 1 is given, area 2 is given, then length L1 and L2 is same for 100 mm. Then Young's modulus is same for 1 and 2 elements, that is 2 into 10 power 5 Newton per mm square. Then P is given, that is 1000 Newton. Okay, so this is a bar element. So bar area of 200 mm square and area of 2 is 100 mm square. So it is a bar element is nothing but it is of rectangle. It is a circular element. So it is made up. It is a round circle. Okay, so it is nothing but diameter. So that is a bar element. Okay, you can imagine it like this. So in this bar we can be fixed at the one end. Okay, other end is giving the load. So it is also called as cantilever beam or whatever it is, but here it is a bar element. So bar element is nothing but one dimensional problem. So how one dimensional problem, how to be classified as, next we are going to discuss. So step 1, finite element model. First you can be classified the this type of problem you can be make into finite element model. So here it is given as a line element. One dimensional element is nothing but line. You can made up of line. So this bar is be classified into this type of model. So here is a F1 and U1. F is a force, U1 is a displacement. Okay, then in part 2, that is F2 and U2, then F3 into U3. Okay, so it is a U1 is nothing but displacement, F is nothing but force. Okay, in point number 3 or as node, we can apply the force. In 2 there is a no force will be applied, but even though you are applying in the unit 3, it be changes in unit 2, changes in node 2. Okay, as well as in 1. In 1 there is a no changes, so because it is 0, so now we can apply the boundary condition at node 1. U1 is equal to 0, there is a no displacement here. Okay, because it is fixed. Then F1 is equal to R1. Why we are put it as in R1? Because it is a, if you are fixing, there is a actual reaction force will be occur. Okay, that is R1. So this type of problem you solved in strength of material by analytical method. Now we are going to solve in numerical method by FEA. So that is a difference. Okay. Then next one is at node 2, U2 is equal to 0 and F2 is equal to 0. So here there is a no force occurs, there is U2 is also 0. And at node 3, U3 is equal to 0, but force is there, that is force F3 is equal to P. Okay. Next, step 2, that is formulation of element stiffness matrix. This is a formulation of element stiffness matrix, that is K matrix into U matrix is equal to force matrix. You know very well, right? So K matrix, I already said K matrix, stiffness matrix for particular bar element or line element, that is AE divided by L, 1 minus 1 minus 1 1. Okay, A is a area, E is Young's modulus, L is length. So that is why K, U and F. Okay, here first element consider, so that is 1 and 2. So that is why A1, E1, L1, 1 minus 1 minus 1 1, then U1, U2. Similarly, that is equal to F1 and F2. Okay, here there is not given any kind of density or any kind of self-acting load. So that is why you don't there is not given in the given problem. So that is why you are neglected. Okay, then next one is you can substitute all the values. Area is 1200 and Young's modulus 2 into 10 power 5. L1 is 100. Okay, then similarly you can substitute here. Then U1, U2, then R1, R2. Okay, so that is element 1 and 2. So 1 and 2 it's given, right? So here force is nothing but reaction force, right? Then element 2, that is 2 and 3, that is U2 and F2, U3, F3, that is the second one. So A2, E2 into L2, 1 minus 1 minus 1 1, then U2, U3 is equal to F2, F3, then 600 into 2 into 10 power 5 divided by 600, then 1 minus 1 minus 1 1, U2 and U3 is equal to F2 and F3, right? So that is 10 power 5 can be common, so that is why you take it outside. Then you can be substitute here the values. Here F2 is 0, F3 is P. Okay, so that is 2 and 3, 2 and 3. The next you can assemble, that is assemble the global stiffness matrix, assemble the stiffness matrix, or as formulation of global characteristics equation. Okay, how do you solve it? That is a diagonally you can be added. Okay, for 1 and 1 it is a 3. Then similarly here there is a no 1 and 1, so that is why I put it as 1 and 1 is 3. Then 2 and 1, 2 and 1 is minus 3, so that is 2 and 1 is minus 3. Then 3 and 3 is there is a no there, so that is a 0. Then 1 and 2 is minus 3, where is the 1 and 2 is minus 3, then 2 and 2 is 3, so that is why I put it as 1 and 2 is minus 3 and 2 and 2 is 2, right? What is given? 2 and 2 is 3, 2 and 2 is 3. Okay, the next in this matrix 2 and 2 is 2, so 2 and 2 is 2, so that is 3 plus 2. Then remaining then what is that? 3 and 2 is minus 2, so 3 and 2 is minus 2. Okay, similarly 1 and 3 is 0. What about there? 2 and 3 is minus 2, 3 and 3 is 2, so you can assemble like this. So 2 and 3 is minus 2 and 3 and 3 is minus 3 and 3 is 2. 3 and 3 is 2. So remaining term is 0. Okay, so how this is why we are going to assemble the this is why we are going to assemble this global stiffness matrix, right? Okay, or else you can be diagonally, you can be added. So it's a first element, so it is a second element, so that is a added in diagonally. Okay, then u1 and u2 and u3, that is equal to r1 0, then 1000. Next apply the boundary condition. Since at node 1 u1 is equal to 0, so you can apply here 0. Okay, so while solving, if you are in this value is 0, then you can eliminate the term first row and first column. Suppose u3 is 0, you can eliminate third row and third column. Suppose in u2 is 0, you can eliminate second row and second column. Okay, here u1 is equal to 0, so you can eliminate first one and second one. Remaining what is there? 5 minus 2 minus 2 2, then u2 u3, that is equal to 0 1000. Okay, 10 power 5. Okay, u2 u3 is equal to 0 and 1000. Now you can be simplify it and get the answer. That answer is u2 is equal to 3.33 into 10 power minus 3 mm. Then u3 is equal to 8.33 into 10 power minus 3 mm. Okay, the next evaluation of element stress. Okay, how do you calculate this stress? We already solved that problem. Sigma is equal to, stress is formula is sigma is equal to Young's modulus into strain. So strain, you know that u2 minus u1 divided by L1, you know that u2 values we found here and substitute in this formula, and u1 is 0 divided by L1. Okay, then Young's modulus value, you know that 2 into 10 power 5, then substitute here and find the values, that is 0.83 megapascal. Then element 2, E2 is equal to u3 minus u2 into L2, so that is u3 value known and u2 value is also known value, then substitute here and find these values. Then sigma 2 is 1.66 megapascal. Right, next we are going to calculate the evaluation of reaction force. So reaction force, so I already told that formula for reaction force, R is equal to Ku minus F, right? Reaction force R is equal to K into U minus F. So that formula can be applied here. So 10 power 5, first one is that is K value, U value, then minus F value, that is equal to R1. So you can apply here 10 power 5, 3 minus 3 0 0 8 power 3 into R1. Then 10 power 5 you can be simplified, that R1 is equal to minus 999 Newton, right? So now you can understand this. While you are applying the load of 1000 Newton, that u1 is 0, then u2, if you are applying load, it definitely be elongate along the vertical direction, right? So if you are vertically elongate, so what will happen of that node 1? Node 1 is fixed, so that is a 0. Node 2 is some elongation, and node 3 is also some elongation. So how do you solve this? So based on that problem, we find this u2 is equal to 3.33 into 10 power minus 3 mm will be elongate, and similarly u3 is 8.33 into 10 power minus 3 mm, it will be elongated. It is clear? Okay, thank you.